Today we'll be discussing self-supervised learning. The first part of the lecture is basically history of self-supervised learning, which isn't all that exciting because it's not state-of-the-art research, but I think it's important from the point of view of it gives us a good lay of the land of what is to come. And sometimes the history is relevant also because it exposes us to techniques which have gone out of favor, but then have a tendency to come back in to new research in different ways. So let me start sharing the screen. Let me know if you folks can see my screen now.
Yep.
Okay. So again, when I say history, it's about papers which are about a decade old, so 2010, 2015, circa that time period is what we'll discuss, and then we'll lay the groundwork for what is to come in the next part of the lecture, the second part of the lecture, which is kind of discussing of a lot of the state-of-the-art techniques. So far in the course, we have talked about normalizing flows, autoregressive models to begin with. Then we talked about normalizing flows. Then we talked about variational inference, and then generative adversarial networks over the last 3 or 4 lectures, right? So primarily the first topic was kind of based on modeling the density of distributions. So that's the autoregressive normalizing flows variational inference. Then it's implicit models, which is GANs, and an explanation for GANs, which is energy-based. And then looked at a lot of different applications of GANs. Now, today what we'll be focusing on is how do we learn representations from raw data, specifically from unlabeled data. And the representations are useful to us because they help us perform downstream tasks, which is things like classification, segmentation, things of that nature in the visual domain, for example. And what do we typically mean by unsupervised? We do a bunch of pretext, that is another term for pretending or proxy tasks. So these are tasks which are not of inherent interest to us. We do them in order to learn the representation that we then use for performing the downstream tasks, which are actually the tasks that are of interest. That's why these other tasks we do in order to learn the representations are referred to as proxy tasks. And the whole field is, what are these different types of tasks? Are there some that are more data efficient? That is, we do not throw as much data at the proxy tasks as other tasks. And how well do these tasks help us to learn representations, which then help us perform the downstream tasks to a good or better extent. So that's the entire realm of the study of what is referred to sometimes as unsupervised or self-supervised learning. This is just an illustration where he tries to show that why do different representations that we learn with the different tasks, why do they matter? It matters because of course, there are multiple reasons, but one illustration of why it matters is to say, let's say we want to separate the data shown on the left, and we want to do it, we want to linearly separate the data that we see on the left. If the data is represented in kind of Cartesian coordinates of X and Y, the task is relatively different or difficult. On the other hand, if we use polar coordinates, which is basically a radius and an angle, then we can very easily separate it because we can just say at such and such radius and between the angle that goes kind of at this point and at that point, or sorry, this angle and that angle, we can kind of say most of the data is located of the blue type is located between those radii and angles, and vice versa for the green. So that representation of the data in terms of polar coordinates or in terms of Cartesian coordinates gives us differential ability to solve the problem that we are interested in. So this kind of begins to hint at, if we learn certain kind of representation, then certain types of tasks which we are interested in can become easier or harder to do. If we just look again at what we know of neural networks and what we have seen in various visual representation studies, it's kind of become clear to us by now that at the level of pixels, all we have are pixels. And as we go deeper into the network of deep neural network, the lower layers, as they are called, help us find edges or help us find things which are high frequency, change quite often and change a lot. And as we go deeper, we tend to find things which are of a semantic nature, faces, animals, things that we can interpret like wheels, a person, and so on and so forth. Whereas the earlier layers are kind of learning high frequency entities or models, and then these layers help to compose these lower layers learned representations into things that then become car, person, animal, and so on and so forth. So we can think of this as every layer writing its own representation that then is composed by the layers which are at the deeper level. So one way, and I guess all this comes from the Ian Goodfellow book on machine learning, one way to think about it is the deep learning is a way to learn the features. And there are different kind of embedded circles, if you will, with example of deep learning being the multi-layer perceptron, and then the shallow autoencoders, which we'll talk about a lot more in the first part of this lecture, help us to learn representation learning. And then we apply it, or we use logistic regression, for example, which is an application of what we have learned in this process. And that becomes machine learning. And then, when we apply that process to certain tasks, then the whole thing can be referred to as machine learning or even artificial intelligence. So as I mentioned before, deep unsupervised learning is basically learn representations of underlying data, but without the help of labels. So we can view unsupervised learning as a subset of deep learning, which in turn is a subset of representation learning, which then is a subset of machine learning. So you can go from bottom up or top down, but basically that's kind of one way of looking at deep learning. And this is just a repetition, but the important and interesting point to note is self-supervised learning is just kind of an analogous term to unsupervised learning. So it's often used interchangeably. And it's called, why is it referred to as self-supervised? Because it uses the data itself without the labels. And how it does that, it creates some pretext or proxy tasks. So these proxy tasks are tasks which we are not really interested in, but we perform them in order to learn the representations that the task generates, which we then use for our task of interest, such as classification, segmentation, and so on. Now, kind of the motivation for self-supervised learning has been the fact that one of the hardest parts in machine learning and the success of supervised learning has been because we've been able to generate a lot of labels for whether it's text, in which case a lot of self-supervised learning is used, but especially in case of images, we require a lot of labels. And as he talks about, there are billion-dollar companies that have been created just to provide or develop the infrastructure to perform labels. perform labeling on variety of data, whether it be MRI, CRT scans, and or images of all different kinds. And so in that sense, good supervision, that is, labeling of images primarily, is not cheap. That's the reason, there have been companies formed to address this challenge. There has been infrastructure built where people are allowed to very quickly perform the task and to help them perform the task in a really quick manner and for large amounts of data. The other motivation for self-supervised learning is the fact that we notice that most children and animals do not learn in a large part by providing labels. They kind of learn by observing people do things, and so that seems to be analogous to self-supervised. That is, nobody very often they learn just by observing other people do different tasks. So while obviously you may not want a little baby watching an Apple video or YouTube and so on, the idea that this saying on the right has is fairly interesting. The source of this is, if you've seen a version of this kind of saying before, which is give a man a fish and you will feed him for a day, and give the man teach him to fish and you'll feed him for a lifetime. This is just a variant of that saying from Pierre Sermonette, probably a robotics researcher, and the saying is, give the robot a label, you feed it for a second, and teach the robot to kind of label itself for self-supervised learning, and it'll be able to feed itself for a lifetime. So just an interesting way of twisting the aspect about learning and convey it in the context of self-supervised learning. And again, this is just a definition, but the interesting part is, so fine, this is all fine and good, but how do we actually perform it? And we actually perform it by the very simple, but variations on this will exist, but essentially by withholding some part of the data and asking the network to predict the data that is withheld from the remaining portions of the data. And there are all kinds of variations of this. And the challenge then becomes, what kind of tasks are those that we can provide to the network, which will help it, and what kind of data can we withhold from the network in order to have the network learn the best representation for the underlying data, right? And that's where the challenges are. What should the task be? How good are the different tasks in getting the network to learn representation that we can then use for downstream tasks? And the idea is eventually to get good semantic features that we want to use for our downstream tasks. So the success so far of machine learning has been largely because of supervised learning, which is a lot of labeling, and having the labels has helped us do some remarkable things in a variety of different domains. So the recipe is clear. We want to kind of match, if we can, or potentially even exceed if possible, the same kind of performance that we get with supervised learning, but not without having any label data set, right? So that's kind of what we are after. Since there is a ton of data available these days, it's more, how do we use that data in order to learn equally good, if not better features without labeling or supervision, and then be able to deploy these systems without relying on too many labels. So sometimes you'll see that a little bit of labels help, so that might be combined with self-supervised learning to get good results. And this self-supervised learning is also could be better because you have a ton of data that you can learn more about the world, because the portion of data that exists with labels is small compared to the amount of data that exists in the world which does not have labels. And it's that kind of a thought which also has led to, if you've seen anything at all in the unsupervised, self-supervised space, you would have seen discussion of Jan LeCun's cake, where he's just talking about exactly the point I alluded to in the previous slide, which is the amount of data in the world, excuse me, is the amount of labeled data in the world is, you can think of it as just the icing on the cake. It's almost the top layer, a very small, thin layer of data. And here in this slide is kind of referring to it as how many bits per sample, and that's about 10 to 10,000 bits per sample, if you will, compared to the amount of unlabeled data that exists in the world, which you can think of as the entire cake. And then obviously reinforcement learning, he kind of in the analogy is referred to as kind of the cherry on top of the cake. But the other important aspect, which this particular analogy doesn't bring about, but it's important to keep in mind, is the reason that supervised learning has been extraordinarily successful is also because the quality of the bits that we get, even though there is less of such information, the quality of the information that you get by from self-supervised learning, that is by providing labels to the data, is much better. So the efficiency of our learning from self-supervised learning is much better. So it's, while we may have a lot more data in the unsupervised learning space, the quality of that data, meaning how efficiently and how effectively we can learn the representation that we are interested in, is probably less. So the point he makes in the class, which I thought was interesting, is while this definitely refers to the amount of data, there's also the other aspect that we need to think about, which is how effective is is just the sheer quantity of data. It's also about the quality of the data that we need to be concerned about in what we are about to do. So the other aspect, and this is yet another slide from Jan LeCun where he expands on this concept, you can think of a variety of this kind of tasks, especially in the video domain, but potentially in multiple other domains as well, is to think of it as if this is time flowing along the x-axis, and if you consider the color, which is this turquoise light blue color, as the future, and this pink or purplish color as the past, then you can have variations of the combinations, which is kind of what the unsupervised learning, especially in a time flow, time series kind of stuff, is all about. That is, you predict the future, that is the turquoise area, from the past. You predict the future from the near past, because this is, it doesn't include all of the past, if you will, just include a little bit of the recent past. You could potentially look at the current video, for example, and we'll see example of that later in the lecture, and then try to predict the past as well from the present. And if you're talking images and such, then you can also, and we saw this already in a sense with autoregressive models and stuff, but unsupervised is you could predict, say, the bottom from the top or the top from the bottom. So these are all variations of what you could be doing with something like video and in a self-supervised manner. Okay, just gives you a visual representation of various things that could be attempted in a self-supervised manner. So the rest of the lecture, we'll kind of be looking at the various attempts that people have done And most of the first part of today's lecture will be on the history and how we get to the state-of-the-art techniques, which are these contrastive predictive coding techniques. And within that, we'll particularly in the next lecture look at instance discrimination and kind of various techniques of various SOTA techniques. But today, what we'll be looking at are reconstructing data from a corrupted or partial version of the data. So things like denoising autoencoders, inpainting, colorization, and then we'll get into the next set of things that people use, the next set of proxy tasks, which are relative patches and their location prediction, how to solve jigsaw puzzles, and then rotation, which will kind of get us to contrastive learning. The basics of contrastive learning are foundational or founded on the word-to-vec concept as applied to text learning. So we'll go through all this, set ourselves up for what is to come in the next lecture, which is contrastive predictive coding. So that will be kind of the lay of the land of today's lecture. And if we go to the next slide. So we all are familiar with the denoising autoencoder, where there is an image of, let's say we just start with MNIST, the simplest of data that we begin to work with, and it's a picture of the number 2, try to add noise, push it through an encoder into a latent space, which obviously is less than the number of dimensions. The latent space dimensions are much less than the dimensions of the data, push it through a decoder and recover the original image. So the hope is that the encoder will kind of capture some inherent representations in the latent space, which the decoder can then extract. Now, why do we add noise? We add noise because if there is no noise, then this whole process just learns kind of the identity mapping. But we want the representation to be better than just learning identity mapping. We want it to learn something underlying about the data, if you will. And in order to do that better, it kind of we add a little bit of noise to the input. Right? This is where he kind of gives a conceptual interpretation of what this denoising autoencoder does, which I thought was interesting. Actually, it's not these two slides, it's this slide, where the point he makes is you can think of the MNIST data as, the setup of the autoencoder or the denoising autoencoder as trying to find a hyperplane of the data manifold. So if you think of the MNIST set of data as being represented by a manifold, which is an outline of a data of a shape in the multi-dimensions that the MNIST data lies in, then the goal of the network is to find or identify this hyperplane, which is kind of the representation of the manifold of the data. And what the noise addition does is it pushes the points which are on this manifold, which are the MNIST data points, away from the manifold and forces the network to try to learn to put them back on the exact hyperplane of the data manifold. So by pushing them slightly outside, and you do that by adding different types of noise, which we'll see in a minute, but assuming for a minute that the type of noise that's added is Gaussian noise, then what it's done is in the multidimensional space that these points of the MNIST lie, these data points of the images of the numbers lie, then the Gaussian noise is pushing them off, and the network is forced to learn to try and put them back. And in the process, it learns not just an identity mapping, but a mapping of where in general the data points lie for the MNIST in the hyperplane of the data manifold. So that's kind of what is going on when we apply a denoising autoencoder to something like an MNIST data. And again, this is covered in this Vincent et al. Paper in 2010. And as I said, it's been, we are in 2021, so we are about a decade plus away. So this kind of begins to refer to why I said that, the first part of the lecture is a little bit of the history of how we got to where we are today with state-of-the-art techniques of self-supervised learning. The different kinds of, so this slide basically is saying that the loss for denoising autoencoder is typically set up so that you have two different parts to the noise. The first part is for the noise of those points X which are which have noise added to them, and then this is the second part, which is for the points which do not have the noise added to them. And what we want to do potentially is give them different weights and weigh the points which are having noise added to them a little bit higher than, and therefore prioritize the noised points more than the denoised points. Apparently, that's the technique that was used in this paper in order to recover the underlying data representation. Okay. Now, here is an interesting slide, which I was, for example, not aware of, that before multitude of techniques which we are very familiar with and are most taught as basics in supervised learning today, which is, the use of larger batch sizes or use of special initialization to the network, let's say residual networks and so on and so forth. The idea of the stacked denoising autoencoder is you start with the basic input pixel, then go through an autoencoder, a denoising autoencoder, get a hidden layer, go through yet another denoising autoencoder, get another layer, push that through another layer of or denoising autoencoder, get another layer, and then right at the very top, just put in a label, the representation that I've learned, and then predict. So what is fascinating, at least to me, what I found interesting was apparently this technique of stacking denoising autoencoder and then just sticking at the very top classification or some other label task is the way that deep learning was originally performed, even for standard supervised learning. And the reason for this is because deep learning, meaning learning with a lot of stacked layers, was not possible without a lot of the innovations that we take for granted today, such as the specialized initialization, specialized optimizers such as Adam optimizers, including momentum techniques and things like that, batch norm, for example. These were all not part of the tool bag, if you will, of even supervised learning. So way back, it seems, in the 2010s or even before that, supervised learning even was performed by using a set of stacked denoising autoencoders, which I thought was very fascinating in the sense that sometimes if you just learn, modern deep learning and so on, you would think that autoencoders arrived after kind of supervised learning and so on. It was interesting, at least to me, that the stacked denoising autoencoder was a way by which even supervised learning was performed in the past. So it seems like the whole thinking around autoencoding and denoising autoencoder existed even before supervised learning, or in order to even get supervised learning with a lot of layers to work properly. But again, these are not the best of techniques to use under the current infrastructure, meaning with a lot of techniques that we have now learned. Obviously, stacking denoising autoencoder is not the best way to get to where we want to go. And of course, there's different amount of noise that you add and the results that you get. So if you have no noise, you get this kind of result. And as you begin to increase the number of the amount of noise that you add, you begin to learn better representation. But there is again an upper bound, because if you add too much noise, then the network is unable to extract the underlying representation as the signal to noise ratio gets terrible. So there is some bound. This is a picture of individual neurons and what they're learning under the various amounts of noise. And all this obviously comes from the Vincent et al. Paper. And different neurons and what they learn, and you can begin to see the outlines of the number 6 here. Right, and again, this is just various different networks, or various different layer that is stacked on top of the learned representation, and the results that you see no longer kind of relevant, if you will, or even much interest nowadays, because MNIST is obviously a very small data set, and these are all techniques that were relevant or gave us some results, but it indicates the different amount of results that you get with different techniques applied through denoising autoencoders. The next set of the next paper that they refer to in this journey, which helps us progress towards the state of the art, is Pathak et al. 2016. And the goal of this paper is to predict a missing piece of an image. So for example, you take this chunk of this image of a building, and you have the network predict what is missing. And in that process, the network learns an underlying representation of the data. Okay? So that's kind of the hide a portion of the image and predict the hidden portion. And these are referred to as context encoders. Right? So the idea would be to mask a region of the image, and then encode the image with the mask, and the decoder reconstructs the actual image. And so you can kind of say, hey, in computing the loss, you focus only on the or you ignore all of the unmasked data, because that is not what you're generating. You're generating only the masked portion, and you compare the reconstruction loss of just the masked data and use that to train your network. So in this case, there is no labeling, because you just take a chunk out and you make the network learn that or predict the chunk. Right? So the image provides its own supervision. Now, there are various instances of this predict the missing pieces approach, which we'll look at. As I said, it's context encoder. So you take a chunk out of this image, which shows people playing American football, encode the features, channel-wise fully deconnected, and the decoder with the loss is supposed to predict this missing chunk. And obviously, you compare it with the actual real missing chunk that you can put here and have the network predict, have a loss, and that will help you gain the underlying representation. And you take out this encoder subsequently after the training is done, and you apply it for the task that we want to do. So that's kind of the purpose and technique of context encoders. And there are a variety of different ways by which this can be done. You can kind of take a central chunk. You can take some random block of chunks. You can potentially mask, let's say, a player in which, a single player, if you will, or a couple of different players. So you could have a random block, a random region, a central region, different kinds of things that you can do and see which of those help you learn the best representation of the underlying data. Now, the interesting part about this whole technique is what is the kind of loss that you use. So ignoring, all of the math, the intuitive understanding to get is, one of them is obviously the reconstruction loss. So that, for the reconstruction loss, you can think of it as the mean square error between the pixels that your network is actually predicting versus the actual pixels. And you can think of the M here as basically the mask. So this equation in a conceptual word sense is just saying, take all of the mask portion of the image, and obviously we are concerned only about the loss between the mask portion and the portion that the network predicts for the mask portion. And you just take the L2 norm of that in order to construct the reconstruction loss. The thing that they found in the paper is they have apparently tried L1 losses and L2 losses and so on and so forth. And one of the things they found worked well is not just using the reconstruction loss, but also using what we have seen to be the adversarial loss in a GAN sense. So how do we use the adversarial loss? Well, we do have, if I just pointed to, we do have what we would consider in a GAN setup, the real image, which is the portion of the image that has actually been masked out. And then we obviously have the generated image, which is the predicted image from the decoder. So if we think of this as the output of the generator, and this is the second input to the discriminator, so you provide the output of the generated, which is in this case the prediction and the real, and then optimize it through a discriminator, then that's kind of the GAN loss setup or the adversarial loss setup. So not only do you use the reconstruction loss, which is to say how accurately are we reconstructing the original image, but we also use the adversarial loss that gives the best results for learning the underlying representation and for producing the best output from the task. So that's what this paper apparently shows. And then, here is an architectural detail of the encoder and the decoder. At least for me, it was kind of interesting. I haven't read the paper, but this is the first instance where I've seen, and I don't know why. I'd be curious to kind of find out if the reason they use this and whether they give any particular explanation. First time I've seen an even convolutions. Usually it's 3 by 3, 5 by 7, 7 by 7, 5 by 5, 7 by 7. But in this case, for some reason, they use a 4 by 4 convolution. Be that as it may, they kind of reduce it to a flat 4,000 layers and then, take it through the transpose convolution to kind of generate or predict the masked portion of the image. Take the real image, feed it through this and the generated image. Obviously have the first part, which is the reconstruction loss, take this, the actual image and the generated image, take it through an adversarial discriminator, combine the two losses, and that's kind of what you get. So context encoder, when you apply it, here is an example of what you see if you were to just use the L2 loss. You can see that while the network does predict something in the space, it's kind of blurry. And that's something that they talk about, that typically L2 losses apparently give a fairly blurry output, right? And as you go from the edges of the image to the insides, it gets blurrier. The adversarial loss, if that was the only loss to be used, gives some really weird artifacts in the chopped region. You can see what, that output is horrible looking. It has some blotches, but the combination gives you the best result, which is kind of what is illustrated with the right joint loss of just the L2 reconstruction loss combined with this adversarial loss gives you kind of the best reconstruction of the missing portion of the image. And obviously, as I mentioned before, once this training is done, then you take the encoder from this part and you use it to perform different tasks, such as classification, object detection, semantic segmentation, and so on and so forth. And in the paper, they've used it to perform these segmentation and object detection and so on the Pascal VOC tasks, using the encoder as the backbone of the fully convolutional network. So now you get an idea of how unsupervised learning helps us build underlying representations which the encoder has learned, and then you use that encoder to perform the tasks related to the Pascal VOC benchmark. Now, this slide gives us some of the results. The top row on this slide is the state of the art, again, as of when this paper was published. Could be more, I'm assuming some of these numbers are higher, but it gives a relative picture in any case. So classification is 78.2, detection benchmark state of the art 56.8, segmentation 48%, and the unsupervised learning, again, also pay attention to the pre-training time. It's about 3 days. This is about 14 hours. It gives us, the state of the art here is 58.4 for unsupervised. These guys get it to about 56.5. Detection for supervised is 56. State of the art at that time was 46.6. They get that. And then when it comes to segmentation is where, the state of the art was fairly poor. They have kind of improved on it by about 4% or so. So that's kind of the result of this particular technique of context encoding. But again, keep in mind that this was about half a decade away from us in 2016. But it also shows one other significant thing is the gap was very significant between what unsupervised learning could do or self-supervised learning could do and what you could do from supervised, what you got from supervised learning. So it's 56 versus 78, 44 versus 56, 29 versus 48. And obviously these are the downstream tasks that we are really interested in performing, not the masked proxy tasks that we're doing for the context encoders. Right. Any questions up to this point? If not, we continue to push forward. The next set of tasks are, again, interesting. They consist of predicting one view of the image from another view. So what do we mean by view? We'll get to that in a minute. This is just a representation of the denoising autoencoder. So, you corrupt the data in some way and then try to predict the original underlying data. Right? But we could, however, use the source data, split it in some way, and try to predict the part that we have hidden, do some source separation, as it's referred to, and then predict the part that we have hidden from the network and try to see how good a job we do, and use the underlying representation that are learned by this prediction. So what does it mean in practice? In practice, you can think of it as, let's consider, this is considered, the task that it is referred to as predicting the color of an image from a grayscale image. There's a comment in the chat. Mine just posted the link to the paper that we're referring to. Actually, I'll post at the very end of the, by the way, just for those of you who haven't gone to the source material of the lectures, there's a whole, at the end of the PDF of every lecture, there's a whole anthology of papers that they use for the particular topics. So all of the paper references that they've used are provided in case you're interested. And there's obviously a ton of them. And I believe there is even a location from which you can just download all of the papers that they have referred to. They've kind of provided a place from where you can download all the archive papers. So this particular task, as I mentioned, is one of predicting color from the grayscale image. So you separate the image into a grayscale portion and a color portion and try to predict the color portions of the image, or the color in the image, so to speak, from the grayscale image. Okay. And how do you kind of, if suppose you just have a color image, then extracting the grayscale, you don't need a deep neural network and stuff for it. You just average the pixels, and you just average the RGB pixels, and you can generate the grayscale from the color. But if you want to generate the color from the grayscale, that is something that the network will have to learn, right? So that's the goal of this line of work, that is colorizing. And as we know, there's obviously one way that we are very familiar with representing color, and that's the RGB method. I am also familiar, I think in printers and other things, they use other techniques, YMK, intensity, and a couple of color dimensions. But in this particular discussion, they refer to a technique which at least I was not familiar with, and that is apparently the LAB color space, where L refers to the grayscale-like channel, and the A and B refer to apparently the color channels. And so the goal of this method is to use the L channel to predict the A and B channels, because the A and B channels are the ones that have the grayscale content, the color content, and the L channel is the one that has the grayscale content. So that's the learning to colorize work, right? So here's an example of how they do it, or an example of this technique in application of this technique. Here's a L channel image of this fish, and the goal of the network is to predict the AB channels for this image. And you can see it kind of is predicting certain colors for this portion of the fish, a different color for this guy. You can also see that there is some overlap in color between this portion of the fish and say this region of the background seems similar. So there's some potential for the image or the network to get confused and so on. But all in all, it seems to do a fairly good job if you see the results of what happens. This is the L channel, and then it predicts the A and B channel. And you can see that it's done a fairly good job, especially, here's a dark black, here the color seems slightly different from that. But that's the result that you get from learning to predict one view, which is the color view, from the other view, which is the kind of the grayscale view of things. Now, the variation that they had to come up with, right, is in order to get a better result, is this is the ground truth of the image, the bird that you see in this picture. If you just applied the L2 regression, which is, the MSE or the mean square error between the predicted pixels and the actual pixels in the A and B channels. If you were just to use that as your metric for the loss and use the MSE loss as your loss for the color prediction, then you get this image. But that image seems to lack much of the color brightness and the color intensities and just the goodness, if you will, or the quality of colors in the picture on the left. So in order to do that, in order to improve the results that you get from just using an MSE kind of loss, what they moved to, or what the authors moved to in the colorization, was to use not an MSE loss, which is almost like a regression task, but change the task to be one of a classification task. Now, how do you do that? They did that by quantizing the A and the B channels into kind of buckets, and then using the network to predict the buckets into which the original images A and B channels lie. So instead of it becoming a regression task, it was converted to a classification task. And when you do that, that is when you change the loss to be not an MSE regression loss, but a quantized pixel classification loss, then they found that the results look much better. Of course, the color is not exactly the color you see here on the ground truth, but this bird is much more colorful than what you get from the L2 regression. And again, the important thing here is twofold, right? One is we are interested in the results that this network produces, but that's not, again, our final goal. The final goal is to take the representations that this task helps us learn and apply that to our downstream task. Okay, and that result is better when the loss is modeled as a classification loss rather than as a regression loss. In general, apparently, this is true that in deep learning, if you kind of move from an MSE view of pixel-wise regression to a classification, in general, it tends to perform better. So the AB channels are quantified, are quantized, and then used. Classification is used to predict the quantum in which they lie. And another variation of this similar kind of approach is twofold. The next slide just talks about the math behind what I just said, that is converting the task into not so much a MSE regression task as a quantized classification task. The variation on this approach that they also tried was let the network do the prediction both ways. That is, you have, let's say, the L channels and the A and B channels, and one part of the network takes the L channel, predicts the A and B channels. The other part of the network takes the A and B channels, predicts the L channels, and then you combine them to get the result. And you see, and that is referred to as a split brain autoencoder. And obviously, as I keep repeating, the goal is to get this to be as good as X, but again, the overarching goal though is to use this network or the encoder part of this network to then perform the downstream task. So the encoders here predict the opposite channel from whatever channel that you have provided as input, and you hide the other channels going in there. So you predict both ways, hence the split brain, and then you combine the predictions and you get the output. Right. So this is kind of the end of the first chunk of techniques that we looked at historically towards self-supervised learning. Here's an example of the application of the technique. You kind of take the grayscale, take the color, split it, predict color from grayscale, predict grayscale from color, combine these two, and you get that. And you see the predicted image and the input image are fairly good representations of each other, at least in this example. And that was the L and AB. Here you do it with a different kind of split, the RGB and the HHA, which are supposedly the depth channels. So you take the RGB channels and you take the HHA depth channels. So from RGB, you use, again, it's the split brain. So you use the F1 to predict the depth, and from the depth, you use this part of the network to predict the RGB, and then you combine them, get the output. Okay, so that was the first set of techniques and reference papers that they provide as kind of the initial thing to be aware of, or initial attempts at self-supervised techniques. The next set of self-supervised techniques we learned are much more recent, not necessarily state of the art, but fairly close to them. And these are referred to as kind of the visual common sense tasks, right? So you tend to do tasks, the proxy tasks are tasks that visually related, but again, they are proxy tasks. They are not the tasks you're interested in, but they help us learn very good representation of the underlying data. And this particular paper is apparently a foundational paper. This professor in particular has done a lot of work on self-supervised learning. This guy has even won some awards. He was one of the students, but now he's a professor at, I believe, CMU. So is this Josh. So these two are at CMU now. Alexei continues to work at UC Berkeley. They have done, in this paper that he refers to unsupervised visual representation learning by context prediction, is a very foundational paper. It has a ton of references, and apparently is the first paper to do self-supervised learning on images at a much larger scale. And the simple task that it tries to do is to say, let me take a slice or a block from the original image, and I have a multitude of such blocks, and I want you, the network, to learn to predict the relative positions of the block within the original image. So that's kind of predict the relative position of this image, which is the ear of the cat, with respect to the face of the cat. So how does this look like? This gives you a much better illustration, which is the following, that you take chunks of the image, and the chunks are labeled here. This is the center chunk, and you feed two chunks to the network, and the goal of the network is to predict where chunk 3 is with reference to the reference chunk, which is the blue part. And of course, there are some additional details which we'll get to in a minute, but that's the goal. So if, for example, you were to provide the chunk 8, it needs to say it's the bottom right with reference to this particular center part. If this is the case, it would be, let's say, the top right, and here it would be the top left, and so on with respect to this image. This would be the top left, top right, so on and so forth. And so what you provide to the input, what you provide to the network are these two chunks from the image, right? But a few details that are important to have the network learn the relevant stuff is, and that we'll get to in a minute. This is basically the setup of the problem. There are 8 possible locations, as I just showed you. You pass the 2 chunks to CNNs, classify, and make it identify which of these 8 possible locations this particular image is with respect to the reference. So you randomly sample a patch from the image, sample a second patch, find out by pushing it to the network, have the network identify the relative position of one patch with respect to the reference patch. a couple of important things. The network does this task very easily if the patches were to overlap. So it's very important that there be a gap between the reference and the second patch that you provide. So this, where you see gaps, it's apparently very important. And if you think about it, it kind of makes sense. If the blocks or chunks were to overlap, then it's very easy for the network to identify the location of the patches because of that overlap. The second part is something that I can't explain. If somebody on the call has a quick explanation of why this is important, I would love to hear it. It's something probably that is explained in the paper. I haven't had the time to read the paper yet. But if somebody has an explanation of why, I'd love to hear that, which is one of the things that they found in this task. It's important to get good results is to include a gap. The second thing they found important to do is to jitter the patch locations. That is to say, when you provide the patch, they kind of, by jittering, it means like, if you will, a little bit of a shake. So it's almost like adding noise to the denoising autoencoder kind of analogy, right? That is, you don't exactly provide this patch, but you jitter it. And you apparently jitter not just the location, but you jitter the colors as well. So the best analogy I can think of, but I don't know whether it is a good explanation. That's the reason I'm saying, it's probably important to read the paper to understand the reasoning behind it and the logic behind it. But the way I think of analogous to noising the autoencoder, you jitter this patch. That is, you jitter it, meaning you move it or shuffle it a little bit. You still need the gap in location as well as in the color that is within the patch. So I'll pause here. Anybody else have or any better explanation or have read the paper by chance to be able to kind of say why the jittering is so important?
I thought it was because the camera always color shifts certain way, and you can predict where it is just from the color shifts, right?
Oh, I see. So you're saying because ultimately, and we'll get into that in a minute or down the road, that you can think of a lot of these tasks as kind of the reverse learning of the camera position. So you're saying that unless you jitter it, just like the overlap, if you don't jitter it, then you learn things about the camera, but not from the patches.
Yeah, you can predict the position from the how the color changes. So in this corner, the purple shifts, and so it will learn the position of the patch just from how the color behaves. So instead of learning the structure, it will learn the lens character. Yeah, I think that's what he said. But
so that
yeah,
the image
that's probably it.
Right demonstrates it, correct? So it's kind of
this guy, right?
You can see that So is that correct?
Yeah, that's what I was saying.
Is that right, Motin?
Yep. That's what I was trying to say, is that it predicts the position based on the lens character than the actual thing in there. So yeah, and then the picture shows it, like how the when you take a picture, it looks, instead of white, it looks a little purple and then a little bit green on the side, and you can see which side the edge has green, and then you can predict which part of the image.
This guy.
Yeah. So if you have an edge and it's greenish on the top and purple, then it's at the bottom right side. It's kind of, I think that's what.
I see. Yeah, they refer to chromatic aberration. I didn't quite catch on, but that's probably what is meant by chromatic aberration, right?
Okay. Yeah. Probably.
So apparently these two things, that you need to jitter the position and you need to jitter the color, were, at the time the paper was written, it seems kind of important revelation, but apparently now it's a well understood or kind of treated as obvious in a lot of the self-supervised learning tasks, which, you know, for us, or at least me learning this new, still wasn't obvious, but thanks for the explanation, Morten. At least I understand why it's important to do that, because you're not learning what you're after, but you're learning some characteristics of the camera, which then help you to predict. So that will not then translate to other tasks, if you will. So that's the reason why jittering the patch locations and color, actually there should be an and here and the color as well, as he talks about in the lecture. The next common sense visual task after this one that is very often used and provides close to state-of-the-art results from what I recall is, instead of just predicting the relative portions of two patches, you give the problem of solving a jigsaw puzzle of an image to the network and make the network, you shuffle the images, and as you can see, there is, you know, a little bit of a gap between the blocks, and then you shuffle them. So this is like, you know, if as children growing up, at least I played with these puzzle blocks that you have to shift with one empty hole and then get them in the, with numbers in the correct sequence or with images and so on and so forth. So this is the neural network version of that challenge, is to have the neural network kind of predict where the face will be, where the legs are going to be, and where this particular portion of the image is, and have it generate what's on the right from what's provided to it on the left. And the solving jigsaw puzzle task is a pretty interesting task, which leads to quite a bit of good results with learning the underlying representation. Right? Now, how is this actually implemented? Because if we assume if we assume 9 different blocks, then obviously there are 9 factorial possible permutations of this, right? And if we have to have the network predict the sequence of the 9 factorial possible combinations, that would obviously be a significantly large number and fairly complicated task. So instead, what they do, let's see whether the next, instead what they do, let's say we take this car, what they do is they determine the permutations, hash them, give it an index into each of the different permutations, and make the network predict this single index which refers to the permutation. Right. So again, it kind of converts what would have become RNN in order to predict the sequence of these various permutations, and you'll need, you know, something like an RNN or an LSTM. Instead of all that complexity, kind of hash all the results, put them into a table, find the index of that table, and or find the index of the permutation of interest, and have the network just predict the index. So it becomes kind of a classification task. And this is kind of just a representation of the network. And if you say this 1, 2, 3, 4, 5, 6, feed it in, you shuffle, you get it back, and you kind of predict the index into the combinations of permutations. Right? So every single patch of grid passes through a shared encoder, and the meaningful representation is extracted by the encoder, and that encoder is then extracted and used. So that's another, and this is a different paper from the paper that we referred to earlier, but again, as I mentioned, I'll point to the references, and there's a list of references at the end of these slides. And this is a fairly important paper as well in our goal to get towards the state of the art in self-supervised, unsupervised learning, that is solving jigsaw puzzles. Now, the simplest version of solving this jigsaw puzzle, as it turns out, which also provides a very good results, is predicting rotation of images. So in this case, all that we try to do is take an image and predict how much the original image is rotated, and try to have the network predict the angle of rotation of an image from the original image. So for example, these are all different images rotated by different amounts. And the goal of the neural network is to just predict the angle of rotation with respect to the reference image. So this is one such example, which is there's an image, then you send it to 0 degrees, 90 degrees, 180 degrees, 270. Obviously, you can yourself rotate this image, push it through ConvNet, maximize the probability, and you predict which of these the images have been rotated. Now, keep in mind, in this case, it's all multipliers of 90 degrees that the rotation is subjected, that the image is subjected to, and you learn underlying representations that you then use for the task, and we'll look at some results and some comparative benchmarks shortly. So this is the rotation task. The interesting question that he provides an answer to in the lecture, and it's interesting to think about, is why should the network learn anything at all from this task? That is, we are just rotating an image, and we are then saying that from the task, we use underlying representation that the network learns for classification, segmentation, object detection, and stuff. Now, just by predicting the angle of rotation and doing that correctly over time, the network seems to learn a lot about the underlying structure of the image. Why is that? And the interesting kind of, again, intuitive explanation for this is the fact that it's somewhat related to what we just discussed, that in order to discuss in the other example previously, right, of shuffling the box and trying to predict the relative position and so on. That is, in order to correctly predict the rotation angle, what the network has to learn is kind of the inverse graphics. That is to say, what would the camera position and the camera parameters have to have been in order to produce the results that the image is provided to the network is. So, for example, it learns things like the natural position of a face is with the eyes in a particular orientation, the mouth in relation to the eyes at a particular orientation. If we are talking bird and a plant, then it learns that typically the bird orientation with respect to the branches is in a particular direction, so on and so forth. So in a sense, providing a lot of these images and having the network learn this is teaching it the inverse graphics and helping it predict the parameters of the camera that has captured the image, thereby learning physics and gravity and, you know, again, in a relative sense. Obviously, these kind of techniques are prone to error. They can be confused by certain aspects and certain simple aspects of the problem. But that's intuitively the explanation behind why the network even learns anything, just by learning to better predict the rotation of an image with respect to a reference images. Right. So if we did this task for a ton of data And obviously, there's huge amount of images that are available on the web. And if we did through all of the data through our network, then it really learns to perform not only this particular task, but also learns representations that are very useful for performing a lot of the desired downstream tasks. One other interesting data point before we begin to look at the benchmark results. If 4 rotations, given 90 degrees, obviously we'll have 4 rotations, right? 90, 180, 270, and no rotation. But if 4 is good, is 8 better? Meaning if we did it at 45-degree angle, or if we did it just at 180-degree angle, or choose a different combination of 180-degree or 90 degrees, which is 90 and 270, does that give us better results on the underlying to the underlying representation that are learned, give us better results on the downstream tasks? And the answer, interestingly, turns out to be no. So even though naive guess would be if 4 is good, 8 is probably better, we find that if we just use the CFAR10 data set as an example, we get better results with the 89.06% accuracy with just the 4-angle prediction. The 8-angle prediction actually gives us lesser accuracy. And the 2-angle prediction, interestingly, gives even less. And the choice of 90 to 70 gives us even less. That's kind of interesting because some of the tasks, it doesn't mean that you perform a more complicated task that you necessarily get learn a better underlying representation.
I have
and it's kind of interesting
a question about does anyone know how strong is correlation between like a classification using a network as feature extractor? So if we just have this backbone, we freeze it and feed one classification, one like fully connected layer, right? So that's one setting to evaluate this quality of representation. And also what we can do, we can kind of freeze, so unfreeze the whole network and fine-tune a whole network. Is there like one-to-one correspondence in the performance in two scenarios, or might it be different? For example, some network that provides better features for like single layer, like better features to like a linear classifier, and maybe it will not perform as good as when fine-tuned, if it makes sense. If anyone is I believe it's usually both kind of results are published in the recent self-supervised papers, but I'm not sure how does it work.
Yeah, excellent question. Maybe even worth trying to run that experiment with this paper's results. I don't know off the top of my head. Anybody else know the answer to what Arto is asking?
I think if we take a guess, it depends upon the network, the type of the network that the backbone it has, and the tasks that the initial network has been trained under, if we are trying to fine tune it. So the training data and the network size plus the width of that particular network, these two might be the major factors in determining which kind of a rotation or some kind of a argumentation strategy might work best for a particular downstream task which we are going to perform.
Yeah,
Right,
that would be an
I will
interesting
try
experiment
to
to
find some kind of answer maybe in the papers that are out there. Maybe there are some results in that regard. Some research have been done. I don't know.
Yep, there might be.
And are you saying, Arto, that the more recent one like that SimClear and whatever Moco and those provide both results, meaning with and without fine tuning?
Well, I definitely saw both kind of results with and without fine tuning in some papers, but I cannot like really name particular papers. I just remember that both results are used as like are presented in some cases. Like for example, it can be like this first like as feature extractor results, and another kind of result is like with 10% of labeled data or something like that, you know.
Okay. Yeah, so that is this semi-supervised learning kind of stuff.
Yeah, but still it's
semi-supervised
used to provide some understanding of how good the pretext task is. If you can then use the backbone to learn with a small amount of labeled examples, probably the features are really good, right? But yeah, I'm not sure if there is like.
That's interesting. Actually, the point that you're bringing up is also an important one to emphasize for the other people on the call, which is, what Arto is saying is also very useful. I think they may get into it in the second part of the lecture, but even if not, I think it's important to realize something that Arto said, which is sometimes these techniques are used for what is referred to as kind of the semi-supervised learning, if you will, that is, provide a small amount of labels and see how good of a result you get or how much you can improve the underlying representation and very quickly get to state of the art. And that is also very helpful because in some of the medical domains and stuff, you don't have a lot of label data. So if you can accelerate the getting to state of the art by doing a lot of unsupervised learning good representation, and then providing a small amount of data with labels and get to a very good result, that still is significant progress than the alternative of searching for a lot of label data. So that's something else that Arto referred to right now that I think while we haven't gotten into it in this part of the lecture much, I'm assuming he'll touch on it, but even if not, that's an important point that Arto has brought up.
I think so. In the contrastive predictive coding example, the paper, they gave a slight reference to what Arto is talking about. The CPC B2 paper, that's the data efficiency, data efficient image recognition with contrastive predictive coding. They give a example as to what the data efficient image recognition looks like, combined with the pre-training, the data pre-training or the self-supervised network and the backbones, and what kind of a pre-training that has been applied with respect to the patched data the cut mix and the different argumentation strategies, as well as the
Okay.
yeah, so all of that.
Okay. So we get to that. In fact, that's a good advertisement pitch for joining us next week as well, which is when we'll get into the details of CPC, because I think both from an interest of time and what the first part of the lecture that it covers is just laying the foundations for what Mayank is talking about of the CPC paper. We'll just kind of get to what's the foundational concept behind that idea, and we'll stop there, and then we'll continue next week on the details of the contrastive predictive coding. But before we get to that, let's keep moving. So here is a comparison of the various different techniques and that we have seen so far. Some we have seen, some we have not. But what he does is, in this comparison, is to take the Con4 and the Con5 layers. Is this from the? Yeah, this is from an AlexNet, and Con4 and Con5 layers of an AlexNet, which we put the linear classifier on top, and then we do, ImageNet prediction, which is supervised training, and then you compare how the different things. Now we have looked at context encoding, which is the Dorsch et al. Paper. We have looked at colorization, right? Where does it get us? We've looked at jigsaw puzzles. Where does it get us? And then where does predicting the angles get us? And you can see that this RotNet does a pretty good job with a simple task. It's at 50. The Con4 on an AlexNet is at around 60. The Con5 is at 59, and this is 43.8. And you can see the comparisons of some of the techniques, and these two are again, Began and Nat, a couple of different papers, but you can see that the RotNet gives you significantly better results than many of these tasks, as when you look at the Con4, Con5 layers. And this is, across the various different layers. This is across the various different techniques. And then this is the results of RotNet compared to some of the other techniques. Again, from a simple prediction of rotation, you seem to be able to learn quite a bit about the ability to do the task, although I would emphasize that the gap is still pretty significant. Right. And then here is the ultimate comparison, which is the mean average precision on classification, the mean average precision on detection, the IOU mean intersection over union on segmentation. These are all the reference numbers for ImageNet, and these are all the different papers, not all of which we have discussed, but we can go and look at it. But here is context, here is colorization, here is jigsaw puzzles, here is the split brain, so on and so forth, different types of tasks. Here is the context encoding task. And you can see how well they perform compared to the ImageNet, and you can see the improvements beginning to happen. And just with the rotation task, you can see the gap getting narrowed between these. And also between, when you come to object detection, it's, at least to me, it's pretty incredible that ImageNet labels detection 56.8, 54.4. Of course, the gap in segmentation is still significant. But this task seems so simple, and it's the proxy task, but it still helps us learn so much as compared to full labeling, that it is pretty interesting. Okay, the next several slides are something that he does not discuss at all in the class. So I'll just kind of very quickly touch on it. I just browsed the underlying Google AI blog, which I'll provide a reference to. But again, here is an interesting proxy task for video prediction, from which, again, there seems to be quite a bit of learning that is going on. And so, and in fact, interestingly, this task is used to do, as with all proxy tasks, some other tasks that we are interested in. So what is this proxy task? The proxy task is given a reference frame from a set of frames of video image, predict the color of a particular, say, object from the reference image into all the other video images, which are all in grayscale. So it's a sequence of video images of which only the reference image has the color, and the network is asked to predict the color of a particular object in subsequent video images. Now, fascinatingly, what this proxy task is actually doing, or it's actually used for, I should say, is to identify an object such as this car in all subsequent images. So the task of interest much is object, not identification, but you can think of this object consistency across the video. So if you have a car, then you want that car to be predicted by the network or tracked, object tracking throughout the video. But that's the task you're interested in doing. But that's apparently quite a hard task in video prediction and network use for video object. I forget the term that we use, but object consistency or objects, something with respect to advancing video. But in order to do that task well, you use the proxy task of saying, predict the color of the object from a reference color image that I provide, just one. And if you perform the task well, it turns out that that network is very good at continuing to predict the existence of the object in subsequent images. And there is a Google blog post that I'll provide reference to that talks to this in much more detail. So he doesn't discuss this at all, probably in the interest of time in the class, but that's kind of what the next several slides are. So colorize all frames of a grayscale version. And so here, for example, you provide the reference, and then you kind of advance, and the little girl is doing some gymnastics kind of task and saying, oh, predict the color of the t-shirt that she's wearing, helps you learn the object and continue to predict that object through different frames of the video. So you can see, here's the RGB, color channels, quantized color, some of the ideas that we have referred to in the past. And by tracking either the helmet or, different parts of the image, like the little girl, we are able to essentially track, not just essentially track the object, if you will, through the subsequent frames of the video. And so, for example, if there is an soccer ball and we color the soccer ball in the reference frame to be this purplish color, then if you provide a video of images where the soccer ball exists, the task that you're interested is in tracking the soccer ball, the network apparently does really well if you ask it to colorize the soccer ball from a reference image and then use the learning that it has in order to create a network that tracks the soccer ball. So that's the underlying proxy task in order to track objects in videos, which I thought was very fascinating. So this is why this is very interesting because tracking emerges from colorization. So as you try to colorize or remember the color of an object and predict it from a reference frame to downstream frames, you learn to track the object really well. Without, and obviously the kind of missed out the punchline, which is without any supervision. So you don't continuously provide the object, label the object, if you will, in subsequent videos. All you have to do is tell the network to learn to colorize from a reference, and it learns to track the object. But if you try to track the object in other ways, apparently that is quite hard, and the network doesn't do a good job. So that's kind of the predicting neighboring context. Okay, so the next several slides, I think many of us on the call are quite familiar with. So I'm kind of going to go through it fairly quickly because it's mostly setting up the basis for what we will study in much more detail in the next Sunday's lecture, which is this contrastive predictive coding that Mayank alluded to. But before we get there, what it is, the underlying concepts are best illustrated by the whole word-to-vec paper. So, many of us who've gone through the Stanford 224N course know quite a bit about word-to-vec, but let's just run through the basics of it. Basically, again, this is starting from ground zero of how do we learn word embeddings. You can kind of provide, for every word, you can think of this as the link to the vocabulary, and you can do a one-hot encoding, but that has its own problem because it's very sparse. There is no concept of things being close to each other and so on and so forth. So you can then move to kind of finding out, building up the co-occurrence matrix, that is how often do words occur next to each other, and kind of do a SVD of the co-occurrence matrix and try to build an embedding of the words. So the purpose of all this, again, at a higher level, is to understand the concept behind word2vec, and word2vec is a attempt to convert words into embeddings, which are then useful for a lot of tasks that we want to do in NLP. But again, we are not here trying to learn the details of word2vec, but understand the principles behind word2vec in order that those principles can be extended and applied in a variety of different domains. So that's kind of why we are going back and looking at how word2vec or what are the principles behind word2vec. And in order to get to that, the goal of word2vec is to build good representations of words, good embedding for words in particular in a certain set of dimension or a number of dimensions, and then use that in downstream tasks. So the second step, instead of just doing one-hot encoding, is to use kind of the co-occurrence matrix, do an SVD of it, and then use that technique to build the underlying representations. This approach also suffers from sparsity because we have to then find all sentences in which words occur next to each other. Obviously, we can't prepare something that says, all the words that have ever been written in a sentence. The SVD is an order of 3, if you will, computation cost. It's quite expensive. The words are, there can be problems with words that do not occur frequently. There can be noise from words like D and A and stuff which occur very frequently. So the bottom line is there are a lot of issues with just using the co-occurrence matrix and the term frequency inverse document frequency kind of approach, if you will. And that in turn led us to n-gram models, and n-grams are just, words which occur together with n being either 2 grams would be set of 2 words that occur together, and 3 grams would be 3 words occurring together, and so on and so forth. We use that co-occurrence in order to determine the probability of a word given the words that it co-occurs with, which leads us to this kind of fairly foundational paper. Forget exactly when it appeared, but memory serves me right, somewhere in the 2010 to 13 kind of time frame, I believe. And this is the word-to-vec paper. So what does word-to-vec do? Basically, it does or attempts to do 2 things. One, given a set of words, it tries to predict, let's say we have a sentence, then it tries to take a particular word from a sentence, treat it as the center word, and try to predict the center word from all the other words in the sentence, or a window of words in the sentence. So that technique is called continuous bag of words. So in this case, what it does is tries to predict the center word from all the words surrounding it. And there is an equivalent mirror image approach, which is the skip-gram approach, which is given the center word, you try to predict all the surrounding words in the sentence from the center word. And there's math associated with all of that, but let's just look at the kind of the continuous bag of word models, right? So the continuous bag of word models, all it does is it tries to say that it takes the average, if you will, of the words that are surrounding the center word, and then tries to do a softmax of the actual word that should appear in the center, which is the correct word, and compare it to all the other words from the vocabulary that are not the center word. Now, the softmax of trying to do softmax of the correct center word with respect to all the other non-correct center words is obviously a significant issue, because you now have to consider the probability of all the other words in the vocabulary. So there's a way by which the authors of the paper tried to sidestep it, and there are a couple of different ways that they tried to sidestep the issue of having to take this huge softmax. One is called hierarchical softmax, the other is negative sampling. And the negative sampling basically says that I'm going to take a number of words which are not the correct center word and use that. That's the negative sampling, because it's negative because it's the incorrect center word, and it's sampling because I'm just going to use a sample instead of all of the non-correct words in the vocabulary. So bottom line, what you do is you maximize the probability of the correct center word and contrast it with the sample of the incorrect center words, and you maximize the difference in probability between those two, and thereby approximate the softmax. So that's kind of the CBOW, or the continuous bag of words approach that word2vec uses in order to build a good representation of the embeddings for the words in our entire vocabulary. And going through all that, and this, as I mentioned, is the mirror image, which is the skip-gram approach, right? So having gone through all that, what the embeddings that are learned by going through this process, and there's, by the way, if you're interested in it, and my very brief and probably inaccurate explanation, imprecise explanation of word2vec didn't give you a good understanding, you can go through a ton of excellently written blog posts trying to explain word2vec in great detail. But the result of all of that is you can kind of begin to find that there are, if you use word2vec approach to build the underlying representations, then you begin to see that there are relationships that exist between words that emerge from this kind of embedding. So if you, for example, say capitals and cities, then you find that the distance between Russia and Moscow is somewhat comparable to the distance in the dimensions that the words are mapped into. The distance between China and Beijing is approximately the same. So you can see the plot here and how capitals and words capitals of countries seem to be equidistant from countries. So if you search for a capital for China in a space about this distance, you are likely to find Beijing. And here are some other examples. If you search for newspapers and the city in which the newspapers are published, you can begin to find the relevant information. Same thing with NHL teams, NBA teams, airlines, company executives. So you provide Microsoft and Steve Ballmer, and you provide IBM, you're likely to hit Samuel Palmisano, or at least when this was run, he was the CEO, and so on and so forth with various different companies. And in this case, it kind of said Vernal Vogels, although I believe Jeff Bezos was the CEO then. So there's some error there. And at equivalent distance, you can find, based on mentions, you could find the guy who ran or who was the CTO of OS at that time. So that's kind of the underlying concept of word2vec as applied to the text domain. And these two techniques was what I refer to, that is negative subsampling, and this is the hierarchical softmax. And you begin to find out that there are lots of things that you can figure out, not just about individual words, and this is the fascinating thing, it's also about the phrases. So if you combine Czechoslovakia and currency, the phrase Czech plus currency, you're likely to get these. If you consider the combination Vietnam and capital, you're likely to get these, and so on and so forth. So German and airlines, the phrase combination gives you this, which is pretty good. Same thing with Russian and river, and you see these, right? So the four closest tokens to the sum of two vectors. And as you see, when you add these vectors, then you get the results to be that. So in effect, what this demonstrates is this word2vec approach for generating embeddings for the words is fairly good with respect to some of the downstream tasks that we would like to do with the learned representation from word2vec. Same thing here, just another illustration of phrases. Instead of just combination of words, now we are talking about phrases, so multiple words put together, and that helps us to learn, what, and this is a comparison of different types of models and the duration for which they were trained. And you can see 1 day of training with a 1,000 dimension model is able to produce these kinds of results. Right, so why is all this important? Why this kind of breezy explanation of word2vec? It's important because the next set of techniques, which will lead us towards state-of-the-art in unsupervised learning that we are after, are based on what is referred to as contrastive predictive coding. And think of contrastive predictive coding essentially, conceptually, as applying word2vec kind of thinking, so building underlying representation like word2vec did for words in n dimensions, right, like 1,000 dimensions, and taking that methodology and applying it not just to words, but applying it to multitude of different domains, specifically applying the word2vec techniques to 4 different domains: speech, image, text, and reinforcement learning. So that's concept of word2vec kind of approach extended to the 4 different domains: speech, image, text, and reinforcement learning in 3D is what we'll refer to next and study next. And that's referred to as contrastive predictive coding. Okay, So there are variations of it. And so the key insight in this paper is to learn these representations by predicting the future in latent space and by using autoregressive models. Right. So conceptually, you can think of contrastive predictive coding as nothing but extending the methodology of word2vec to domains other than text, speech, image, and reinforcement learning. So that just laid the foundation for what we will focus on, starting with the next slide in the next lecture. Okay, the 5 minutes left. Any quick questions or comments?
Well, another quick question from me. So it's often the humans are referred as an intuition behind many machine learning techniques, and the unsupervised learning is not exception here. So I wonder if anyone has some good references to some research of how the unsupervised learning occurs in human brains. I mean, how this image of the world is built up. Maybe someone encountered some kind of review paper, or I don't know, something like that. More like from I don't know, neuroscience perspective,
cognitive
but
science
like
kind of
mechanistic way. I mean, some.
I don't think they know. At least, I haven't seen anything.
Yeah, I have a couple of people who kind of, or I know of a couple of people, Ato, who work in that space. So I'll poke around to see whether there is any survey paper kind of stuff that compares the two. Just as a reference, an interesting podcast I listened to the other day, unrelated completely to this, but there's a child cognitive psychologist at UC Berkeley who is working with Peter Abil and with the Alexei, trying to bring child psychology or child cognitive science into robotics and the interaction between the two. So, I forget her name now off the top of my head, but she and her writings would probably be a good potential place to look into.
Oh yeah, that would be interesting. Yeah, I also there is this free energy approach by Freeston, I guess, and it might be somewhat related, right? And there is also that thousand brain view of human brain, and it also has some. I think it might have some insight on this, but I'm not deeply familiar with both. So I was wondering if anyone has if anyone have encountered some kind of a review of how to approach all this field. It would be helpful. Yeah, thanks.
So Arto, you mean like neuroscience or neuroscience or cognitive psychology perspective, like doing experiments?
I'm more interested in this what I kind of mechanistic view. So how the process happens in terms of mechanics. The processes. What kind of signals do we have, if it makes sense?
One other thing, Arto, I'll send you. Actually, there are a couple of books written by a French. Now I'm missing whether he's a cognitive psychologist or, as Mochen said, whether he's a neuroscientist. But there is a French guy who has written multiple books about the parallels between human learning and machine learning. And I started reading one or two of his books, but then I kind of got distracted. But that might be a good source. I'll send you the link offline.
Yeah, great. Thank you.
That guy's writing but is very fascinating.
Okay, cool. Thanks.
I've read some or podcasts and, that or some blog posts that talk about the neuroscience aspect of it and how they have different mechanisms. Like if you that are not. There's a researcher here in Pittsburgh, University of Pittsburgh, who I had a discussion with, and he teaches mathematics, and he said, well, I do neuroscience, but all the neuroscience I do doesn't translate to deep learning. It's completely different. The mechanics are different. And he's saying, well, maybe it can turn into computation model, but it will be different than deep learning model. And so I had a good discussion with him about it. But then I think the neuroscience part is very, it's different. But that's my impression, a very limited impression. I will try and find his page.
Yeah, cool. That also sounds interesting. And yeah, that would be nice to see.
Great. Thanks everybody for joining, and I'll see you all next week.